just want to touch quickly, okay, on the idea of adding vectors with components, right? Because as I said before, you cannot mix x and y, right? You can't add x's to y's, you can't add y's to x's. But what you can do, so if I have two vectors like this, right, it kind of looks at first like, oh, how am I supposed to add this to this? They're in two completely different axes. You can even go backwards like that, right? And so backwards in the x-axis, I guess, and even down if we wanted, right? How do I add these? Well, we would have to separate them into their components, and then their components can just add fairly simply, right? So if I show all of their components, then you can see, okay, this one's coming down, this one's coming backwards, but if I add up all the x's like that, right, add up all the x's tip to tail like we always do, well, then I can kind of see, okay, overall, what is the resultant force in the x-axis? It's there, okay? I can do the same thing in the y, but first I'm just going to show the sum. Okay, so this is the sum, the resultant, the net force. Sure enough, look, it matches perfectly. The x components match. So what is the x component of the resultant of these three forces, of the net force when you add these three forces? It's the x component of force 1 plus the x component of force 2 plus the x component of force 3, giving me that resultant x. What's the y component? Well, what's this resultant y component? What's the net y component? The y part of the net force? Well, you take all those and you add those tip to tail, right? So tip to tail, and then let's look, does that match up with our y component? Aha, it sure does, right? From the beginning of the first y to the end of the last y, that is our resultant y force, okay? So this works overall because of the fact that it works in each axis. So that is why we need to make sure we separate x's and y's and then only add x's to x's and only add y's to y's. So notice it works overall for the entire resultant.
Okay, so let's now, knowing what we know about x and y components of vectors, consider this thing they've asked us to consider here. Um, it asks, how can the person apply more force to move the dog but not exert any more force themselves? So in other words, how can they better move the dog without pulling any harder, right? So let's just think about it. What are they doing here? Well, they're pulling the dog at some kind of angle, right? So there's the force they're applying to the dog. But what part of the force is actually going to move this dog, right? Is this person trying to pick the dog up, right? Is the y component important, or are they trying to bring the dog this way, right? Well, they're trying to move them this way. They're trying to make them walk that way with the person. So when I draw the components here, right, we have the x component of the force and we have the y component of the force that together make up the overall force applied, okay? So again, when we look at it, this part, the x force, the x component, that's the part that actually matters. That's the part that's going to make the dog move. You don't want to lift the dog up. You want to pull them, right? You want them to move horizontally. You want them to walk with you. So how can we make this bigger, this bigger, the x component bigger, without pulling any harder? In other words, without making the force applied any bigger. Well, what if we make this angle here, theta, okay, what if we made theta smaller? What would that do to our x component? Okay, or conversely, what if we made it bigger? What would that do to our x component? So if we make it smaller, I'm not going to make FA any bigger. It's going to be the same size. I'm going to at least try to draw it that way. Okay, so that's still the same force applied. Okay, but we'll notice now when I draw the x component of the force applied, it's grown a bit, right? It's a little bit bigger now. Same force applied, but more of that applied force is now in the x-axis. We're not wasting as much of our effort in the y-axis. So it's not quite as apparent there when you look at the x and the y components. But again, we can kind of take this to our simulation here, right? But again, we can kind of take this to our simulation here. If you don't believe me, right? We'll take some force, okay, this person's force, and let's look at the components. I'm going to try and keep it roughly the same size, right? So let's say they're pulling like that. They want this part, the x component, to be maximized so that the dog comes more easily, right? We don't lift the dog, we pull the dog. So if I go and try and bring it down, look what happens to the x component. As I make theta bigger, look what happens to the x component. Now I'm just lifting the dog, right? So as I make that angle theta smaller, look at how the x component grows. Okay, I'm trying to keep the vector roughly the same size. So bigger x with a smaller theta, smaller x with a bigger theta. Okay, but at no point am I pulling harder or less hard or anything. I'm just changing whether my force is expressed through the x-axis mainly or through the y-axis mainly. Okay, so to answer our question of how could this person move the dog without working any harder, they could decrease the angle they're pulling at, right? So decrease this angle theta, make it smaller so that more of their applied force is happening in the x-axis. So I would just say increase x component of their applied force by decreasing theta, where theta is the angle between the applied force and the horizontal. All right, let's now apply these vectors that are not necessarily along perfect north, east, south, west components. Let's apply them in an example here. So as always, we're going to draw our three diagrams: representational, free body, and vector addition. A filing cabinet must be moved into a corner. George pushes with 600 newtons due north. Phil pushes from the side with 600 newtons at 82 degrees east of north. Okay. What is the resulting force, or F net? Right. Resulting force means F net acting on the filing cabinet. So let's draw our three diagrams. We have our representational. So looking from above, what does a filing cabinet look like? Pretty much just a square. Okay. So first, let's draw George. George is doing it 600 newtons due north. So let's label that FG, okay, at G for George. So FG for George. How is Phil pushing? Phil is pushing from the side with 600 newtons at 82 degrees east of north. So up here, let's just think about what does 82 degrees east of north look like? So we have to make that angle, right? So to make that angle, we're going to start at north up here. If this is north and this is east, start at north and we're going to go 82 degrees east of it. And that's where our vector will be. That's pretty far, right? That's 90 would be all the way to east. So that's kind of what the vector is going to look like. Where that little small angle there, what would that be? Well, remember, if we went all the way 90 degrees down, that would be to all the way to east. So if we only went 82, what's left? 8 degrees, okay? Or we have this angle here. We could think of that as 82 degrees, the way they gave it to us. So let's draw George's vector. He's pushing from the side, okay? So if he's pushing from the side, which side does he have to be on? Could he be over here and be pushing that way? No, he'd have to be pulling, but they said he pushed. So he'd have to be over on this side, okay? So 82 degrees, not quite due east, just a little bit up from due east, okay? And that's going to look something like that. Oh, that's probably too much, okay? You don't have to break out the protractor or anything necessarily, but try to be reasonable. If it's a small angle, make it look small-ish, right? And that is FP, P for Phil, okay? Let's just quickly break up that into its x components visually so we can kind of see what that means. So we have our y component there. That's Phil's force in the y-axis. And then we have the x component of Phil's force there, right? That is F Phil in the x-axis. And what is the angle here? Okay, well, he's pushing at 82 degrees east of north, so that is 82 degrees, right? We could have drawn x and then y, and then that angle there would have been 8 degrees, okay? But I chose to draw y and then x. Okay, let's move on to our free body diagram. Free body. So we simplify the situation, we get rid of all the extra kind of beautiful artistic details, and we just strip it down to a single point. So we're going to let that single point represent the center of mass of the filing cabinet. Let's draw Phil first. Okay, so Phil, by the way, sorry, just going back for a sec, these should be about the same size. I maybe made George a bit too big, right? Why about the same size? Because they're both pushing with 600 newtons of force. Yes, in different directions, but the magnitude is 600 newtons for each. So
nobody is pushing harder than the other. They're just pushing at different angles. So there is, oh, again, probably too dramatic. There's Phil. Okay, that's F Phil. And then where is George? It's due north. So straight up, due north. Okay. Does George's force also have x and y components? Truthfully, yes. Every vector has x and y components. It's just sometimes the x or the y components might be 0, right? So in the case of George, it still technically has x and y components. It's just that George's x component is 0, and his y component is all of his force. Fg is all y. Okay. And again, I could draw the components here, but then when we do our vector addition diagram, okay, we draw them tip to tail. So first, let's draw the force George applies, force of George. Okay. Then we will draw, whoops, shouldn't use a little g because that looks like gravity. Big G for George, capitalize a first name. And then force of Phil off on an angle that way. Okay, what does this question ask us to find? The resultant force, right? The net force. So picture in your mind now, where does that net force go net force vector go on our diagram here? Well, it goes from the beginning of the first vector to the end of the last vector. So that there is F net, or F resultant. That is the result of George pushing to the north and Phil pushing at 82 degrees east of north. What do you get as a result? You get this net force here. Okay, so I think of these problems as building the resultant triangle, or building the F net triangle. What do I mean by that? I mean, if we can build the triangle that makes up F net, then we can solve this problem. What do I mean by that? The triangle that makes up F net? I mean, look at F net here. Hey, that's a vector. It's an F, it's a vector. So it has an X component. That's F net X. It also has a Y component. That's F net Y, right? If we can build this triangle, if we can figure out these components, then we can use Pythagorean to get the F net, which is the whole point of this question, right? Remember that since it's the X and the Y axis, that's automatically a 90-degree angle, okay? Let's just put, eventually we'll need to say the direction of F net, so we'll call that our theta. That's gonna be the angle that we're interested in when we try to communicate the direction in which F net is. Okay, so how do we know how big F net is? F net X is. How do we know how big F net Y is? Well, where did F net X come from? What I mean by that is, how did we get F net X? What had to come together? Well, it's just the X components of every vector that makes up F net, right? If we take the X component of this vector and the X component of this vector, add them up, hey, that's our overall F net X. So I just want to draw, these are not absolutely necessary, but they do kind of help to imagine. What if we do a VAD now in the X axis so we can figure out, hey, where did F net X actually come from? Well, F net X, did FG contribute anything to F net X? Is any of this sideways force because of George, right? And when we look back, no, we kind of see that the only thing with an X component here is Phil, right? So what is F net X? Well, here's F of Phil. And so there we go. That's a VAD in the X axis, right? We're adding up all the X components. So there's F net X. And it just so happens to be the same as the force of Phil, right? Which we might have kind of figured by looking at the scenario anyway. What about in the Y axis? Because we can add our vectors in the Y axis too. So what about VAD in the Y axis? What does that look like? Well, again, where did F net Y, this guy right here, where did that come from? Again, it came from adding all the Y components of every vector along the way that made up F net, okay? So where'd that come from? It came from George, right? George definitely has a Y component. In fact, George is only Y component here, right? George is all Y. So George, that's definitely a Y force, F George. And then does Phil have a Y component, right? Well, look at him. Yeah, he does. He's not just pushing in the X-axis. There's a slight northward push coming from Phil too. I think I said George. I meant Phil, right? There's a slight northward push coming from Phil as well. It's not as big as George, but it's there. So that would be tip to tail, right? There's our additions in the Y-axis. And so this F net Y, where did it come from? It came from
these two y components. And so our resultant, our Fnet in the y-axis, looks like that, okay? We are saying with a diagram here, something we are going to say with math in a second. Now, it's important to understand, though, a vector addition diagram is an equation. We are saying that Fnet x is Ffill. We are saying that Fnet y is Ffill y plus Fg. And that's, sorry, not Ffill x, okay? Going back to that, anything I said about Ffill, I was talking about Ffill x, okay? Sorry about that, because he's not entirely in the x-axis, but this is the x component of Phil's motion, okay? This really is all of George's force because it's all in the y-axis, though, right? So when we say that F net y is going to be the George's force plus Phil's y force, this is it's a visual way of representing a mathematical reality, okay? How are we going to solve this? Like I said, I think of these as we need to build this triangle, this colorful triangle here, this purple with the red and the blue. Once we've built that triangle, once we've figured out F net x and F net y, well, then finding F net is just a matter of Pythagorean theorem. So doesn't matter which one we do first. I'm going to choose to do x first. So step one, okay, and you don't have to think of it necessarily in broken up steps, but can kind of help to organize your thoughts a bit. But always a good idea to tell me what you're doing when you're solving a problem so I can kind of follow your thought process, right? Find F net x. So I'm going to write this down because this is how we're going to solve every vector addition problem we ever do, okay? And any ones you've already done, you've already kind of followed this process. We're just using forces now instead of something else. So where did F net x come from? It came from the x component of every vector along the way. So it came from Fpx, Phil's x component. It also came from George's x component. And right now you're probably saying, but George doesn't have an x component. Yeah, you're right, he doesn't. Okay, but this is still true. F net x is still equal to those. It's just that what's what's the x component of George's force? It's 0. So we won't worry about it, but I'm just showing you that this is always the idea. F net x is F1x plus F2x plus F3x plus F4x, on and on and on until you've covered every vector. Okay, so then F net x equals Phil's force, but the x component of it only. So what is the x component of Phil's force? So I'm just going to draw so we can kind of visualize it again. Let's draw Phil's force over here so we can kind of visualize what we mean by the x component. Okay, it's not quite accurate, but that's okay. We're just trying to visualize. There's the force of Phil, and that has some, whoops, I'm just going to draw that down here so that we can have some room. Here's the force of Phil. It has some y component up, right? Smallish. That's Phil's y component of his force. But then it has an x component, which again is what we're interested in. There is Phil's x component. And that's just a right triangle, right? Because this is always going to be a 90-degree angle. The x and y axis are always at a 90-degree angle to each other, okay? That's theta. And that's not just theta. I shouldn't call it theta. That is, we know that. It's 82 degrees, okay? Problem told us that. So what is Phil's x component of his velocity? Well, we want Fpx. So to 82 degrees, the angle we know, that's opposite. That's the opposite side, right? And we know the force of Phil, that's 600 newtons, okay, 600 newtons. So we want the opposite, we have the hypotenuse. So if we think about SOHCAHTOA, right, we got hypotenuse, we want opposite. So it looks like so is our trig ratio here that's going to help us out. So then we have that sine of 82 degrees equals opposite, Phil's x component, over hypotenuse, Phil's total force, okay? So doing some rearranging, you can see that Fpx will be Fp times sine of 82, right? We would multiply both sides by Phil's total force. So F net x equals Fpx equals Phil's total force multiplied by, whoops, not cos, sine of 82 degrees. And so now we've got F net x equals 600 newtons times the sine of 82 degrees. If you throw that in your calculator, always leave, I say, at least 4 decimal places, okay? at least 4 places after the decimal, I get 594.1608 newtons. The reason we're leaving decimal places is because we're going to need to use these numbers again later. If we round them now, we're going to carry that rounding through every step, okay? Which way is F fill? X. Which way is the X component of Phil's force? Well, take a look at the diagram, right? That helps us out there. This is to the east. Okay, that makes sense. He was pushing at east of north, so the X component would be to the east. You can probably guess which way his Y component would be based on that, or based on our diagram. Okay, great. Now we got F net X. Let's find, because we're trying to remember, build this triangle here. Let's find F net Y. Again, what is F net Y? What is anything resultant or net Y? It is the sum of the Y components of every force that makes it up. So in this case, it's Phil's Y component and George's Y component. Okay, so simplifying a bit here, it just so happens that if we look over here at, again, bring your attention over here to the left side, Phil's Y component we can get with this same angle again here, except now the Y component is adjacent and we still have the hypotenuse. Yes, we actually also have the X component, but I'd just like to use as many values as possible that were given to me and not calculated by me. So adjacent and hypotenuse, what's my trig ratio? Out of SOHCAHTOA, I want adjacent, I've got hypotenuse. So that would be cos, right? So cos of 82 degrees equals adjacent, Phil's Y component, over his total force, right? Okay, so again, with the manipulation, how would I get FPY by itself? Well, I would need to multiply both sides by F Phil, and so F net Y equals F Phil Y plus F George Y. So F Phil Y, we just kind of worked out, is going to be F Phil times cos of 82, right? When I solve that equation for FPY, cos of 82 degrees. Plus, now FGY, what is FGY? Well, FGY is just FG. It's purely in the north, right? So that's only a y-axis vector. So we can say FGY is just FG. It's all in the y-axis, right? It doesn't have an x component anyway. So F net y then equals, what's the force of Phil? 600 newtons times the cosine of 82 degrees plus George's y component is just George's force, like we said. So plus 600 newtons. And what do you get when you add those together? I got 683.5039 newtons. Okay, now which direction is F net Y? Again, we can go back to our picture. We can also kind of think about it. Someone was pushing north, someone was pushing east of north. Either way, they're both kind of pushing in the y-axis north, right? And so F net Y is that magnitude, but which direction? North. Okay, do you see what we've done here? We've now built two sides of our triangle. We're putting together the resultant or the net triangle. We got F net X, check. We've got F net Y, check, right? So if you got two sides of a right triangle, can you find the third? You betcha. So let's go ahead and do it. Okay, what's our trick here? It's going to be the Pythagorean theorem. So now we've got F net X, we've got F net Y. Find F net. So what's the triangle I'm talking about? Again, here's F net, here's F net X, and here's F net Y. So c squared equals a squared plus b squared, Pythagorean theorem. So F net squared equals F net X squared plus F net Y squared. Okay, we don't want F net squared, we just want to know what's F net, so let's square root both sides, and F net equals the square root of, I'm just going to go ahead and put in F net X. So F net X we have was 594.1608 newtons. Don't forget to square it. Plus F net Y squared, 683.5039 newtons. Also squared. Didn't leave myself much room, but also squared. Okay. And so when you type that into calculator, if you do it carefully, okay, you get that the net force, the resultant net force is 905.6515 newtons. Just leaving a few extra digits there in case I might need them later, although for this problem I don't believe I will. Now, are we done? Can I put a box around that? Okay. No, I've been kind of dropping it, but you got to remember force has a vector, right? If you look on your formula sheet, it's got an arrow, but force is a vector. Direction matters. So this is not a whole force. This is the magnitude of the force, but we're missing the other important component of a force, of a vector, the direction, right? Two ingredients for a vector are magnitude and direction. How do we communicate the direction here? Well, we're going to need to use theta, right? We cannot just say northeast or east of north, whatever. How far east of north or how far north of east? And the only way to communicate that is with an angle. So looking at, I'm going to go back to this diagram here where it's just a bit more simplified. Looking at this angle here, which is how we're going to communicate which way F net is, okay, what can I kind of use here? Again, I've got all three sides. I've got F net, I've got F net Y, I've got F net X. Again, just my kind of, my nervousness, I guess. I like to use the things that were calculated with the least calculated values. So what I mean by that is I calculated F net with F net X and F net Y, whereas F net X and F net Y are kind of one step back in terms of things I needed to calculate them. You know what I mean? So I'm going to use F net Y and F net X to get theta. That's just kind of my my paranoia, I guess you could call it. Okay, I like to do that. I find it simpler too to just say, okay, so theta is here. I've got F net Y. I've got F net X. Think about your trig ratios. What's going to help me out here? Okay, how do I get theta? Well, I'm scrolling up so you can see SOHCAHTOA. What in triangle terms, which side is F net Y to theta? Well, it's opposite from theta, right? And what about F net X? It's close by. It's adjacent. So I've got opposite and adjacent. OA, right? That means I want TOA, tan. Okay, so then kind of our final step here, call it step 4, find theta. And so tan theta equals F net Y over F net X. Okay, so to get theta, right, I kind of have to do the opposite of whatever is happening to it right now. What's the opposite of having the tan taken of you? It's taking the inverse tan of you. Okay, so theta will be equal then to the inverse tan of F net Y over F net X, opposite over adjacent, which will be equal to inverse tan of F net X was 590, whoops, 5. Okay, so the inverse tan of 594.1608 newtons over 683.5039 newtons. Okay, the newtons do cancel out, which is good because a trig ratio is a dimensionless thing, right? And so when you do that, you should get that theta is equal to, be careful to hit second function tan, okay? Second function tan, very different than just tan. Also, a reminder, your calculator needs to be in degrees, not radians, okay? So I got 49 degrees. Okay, now even that's not quite complete because we got to think 49 degrees, sure, where, right? Which way 49 degrees? So when you're looking at this, theta is always between either north, east, south, west, and your resultant vector, okay? So is this one between north, east, south, or west and your resultant vector? Okay, which one? Well, it's between east and our resultant vector, okay? Which way is it from east? It is north of east. It's north of east. So theta equals 49 degrees, and it's north of east. We started at east and we went north of it. So it's north of east. Okay, take this, put it here, and now we'll have a complete answer. So rounding to the proper number of sig digs, the net force is equal to, I was given 3 significant digits in the question. Angles have some weird sig dig rules, so we kind of defer to the other quantities. So we have 3 in each of our forces, so I would round 905.6 to 906 newtons. And what's the direction? It's 49 degrees, 49 degrees north of east.
That is the net force. Okay, so honestly, that last question was another application of Newton's second law because we had a net force, right? So that object would have accelerated, okay? Now in this one, this is a true Newton's first law example because assuming a constant velocity, okay, right there, constant velocity. This is a big student mistake. Okay, constant velocity, so there must be a net force making it move. No, a net force doesn't necessarily make you move, it makes you accelerate. Just moving, if you're moving at a constant velocity, if you're not changing your velocity, are you accelerating? Okay, and if you are not accelerating, can there be a net force, right? If A equals F net over M and A is 0, can F net be anything other than 0? Right? No, it can't. We could rearrange that. F net equals MA, right? If A is 0, F net is automatically 0. Doesn't matter how big M is. Okay. So assuming a constant velocity, what is the magnitude of the force of friction? Okay, looking at this image here. Sorry, the numbers aren't great on my screen. I can see them on my paper. Hopefully you can as well. By the way, we're on page 9 here in case you're flipping through the book trying to find where we're at. Okay, so remember, if v is constant, acceleration is 0, and if acceleration is 0, therefore F net equals 0. Okay, so if F net is 0, that means, does that mean there are no forces? No, it just means that all of the forces add up to 0. So maybe you have a ton of forces. They just all cancel each other out so that you end up overall with 0 force, right? Think of it like a tug of war. You can pull really, really hard, but if someone on the other side of the tug of war is pulling just as hard back the other way, well then the system, which is you, the rope, and them, does not accelerate, right? It just kind of sits still if you're both pulling equally as hard. So that's kind of what they're doing here now, except they are moving, they're just not accelerating. They're moving at a constant speed. So they kind of drew our representational diagram for us, but we can kind of add our forces in here if we like, right? We have F, let's call this tractor A, let's call this tractor B. Okay, we have the force of A. Maybe I shouldn't use blue because that's going to be my X component. How about, I guess we'll just keep it black for now, okay? We have FA being pulled at that angle there. We have FB being pulled at that angle there. Now, as I've drawn it right now, would this thing be accelerating, just as I've drawn it? Okay, and the answer is, yeah, it would. There's a net force to the right, right? If I'm pushing kind of right, yeah, and kind of right, okay, yes, up and down as well, but there is an overall rightward force here, right, to the right side of the page. Those things would add. They both have an x component to the right. So I must be missing something because this block would be accelerating as I've drawn it now. And I remember, right, okay, there would be, we are trying to move it, so there must be some friction resisting motion. Now, just thinking about it, how big does that friction need to be? In fact, I probably haven't quite drawn it big enough because think about it. There's FA, which has an X component, FB, which has an X component. Those are helping each other out, right? So the force of friction needs to cancel out not only FAX, but also FBX. When we draw our VAD, we'll see a little bit clearer what we mean. So our free body diagram, let's just strip away the excess here. We don't need to actually draw a picture of a tractor, right? We mostly are concerned with what are the forces acting on the block. So force of tractor A is off at this angle here. Force of tractor B is off at the same angle, but downward, okay? Now, they're not perfectly in the X or Y axis, so they have both an X component that isn't 0 and a Y component that isn't 0, both of them. So FAX looks something like that. FAY looks something like that, okay? And we actually know the angle here from the picture they gave us that this angle is 20 degrees. Okay, same thing goes down here. We have, oh boy, this is going to get crowded, sorry. Okay, we have FBX. We have FBY, which is kind of down. Okay, but once again, they tell us that this angle here is 20 degrees. Okay, that's not the best to look at. My apologies. But why are they not accelerating? Because look at FAX.
and look at FBX. They're both to the right, right? So something must be pulling to the left hard enough to not only cancel FAX there, but to keep going and to cancel FBX. So that maybe this thing is moving, but it's not accelerating, okay? And that is our force of friction. Remember, friction is always working against you. If you're pushing something to the right, friction's to the left. If you're pushing something north, friction's to the south, okay? All right, there's our free body. Let's look at our vector addition. Whoa, sorry, let's look at our vector addition diagram. First, we'll do an overall VAD, and then I think this would be a good one to do a VADX and a VADY. So the force the force of tractor A, right, looks something like that. The force of tractor B looks like that because it's the same size, right, and at the same angle but in the other direction. So that's force B. And what do we know about the net force? Is this thing accelerating? No, right? So if it's not accelerating, what do we know about the net force? The net force must be 0. How does that look on a vector addition diagram? If you have a net force of 0, what does that look like on a VAD? Well, it means when you go to draw from the first vector to the beginning of the first to the end of the last, there is nothing to draw, right? There is no net force. That's because the force of friction brings us kind of right back to where we started, right? So if I were to go and draw the net force here, there'd be nothing to draw. Okay, that is our VAD. So whenever you're drawing a VAD for a Newton's first law question where the net force in the end is 0, you should always kind of end up back where you started. Okay, now I am going to draw a VAD in the X and a VAD in the Y. So in our VAD in the X, we have FAX, right? This thing here. So we have FAX. We have FBX, which is going to be just as large because this is actually the same triangle, just flipped over, right? Same hypotenuse, same angle, just flipped around. So FBX, which is just as big. And then if there's no net force overall, there can't be a net force in the x-axis, and there can't be a net force in the y-axis. So both of them have to add up to 0. Why do they do that? Because there's the force of friction. Okay, force of friction in the x, sure, if you want to call it that, but the force of friction is entirely in the x-axis here anyway. Okay, so the vector addition diagram in the y, what does that look like? Well, again, if there's no net force overall, if this thing isn't accelerating, then it can't be accelerating in the y-axis either, so there can't be a net force in the y-axis. So let's go ahead and draw our VAD there. And what do we already kind of know? We already know we have to end up, so to speak, back where we started, right? We have to have no net force in the end. So there is FAY, right, kind of up. And then FBY, if you look at it, yeah, it's about the same size, but it's down. So when I go to draw my net force there, I go from the beginning of the first to the end of the last, and oh, there's nothing to draw, okay? All right, so now I think we're ready to jump in and kind of start solving it. So the approach here is a little bit different than last time where we're trying to build that resultant triangle because there is no resultant triangle, 0, okay? But that actually makes the analysis a little bit easier if I'm being honest, because now we just set everything equal to 0 in the x-axis and the y-axis, and then we can find out what we need, okay? So we're looking for the force of friction, okay? So first of all, let's find Fnet x. Now I chose x here. I want you to think about why, pun intended. Why did I choose to not look at the y-axis? Well, does the force of friction, FF, does that have a y component? So this is canceling out with this, FAY is canceling out with FBY, but is showing that going to get me any closer to finding the force of friction? Well, not really, right? That's not going to help me out. So I need some expression that has the force of friction in it, okay? So Fnet x, let's start here with Newton's first law, equals 0. Okay, this is physics principle. It's actually, if you look on the back of your formula sheet, physics principle number 0. Okay, Newton's first law. This object does not have a net force acting on it, so it is not accelerating. Well, what is F net x? Like always, it's the x component of every vector that is, of every vector, the x component of every vector that's coming together to make F net. So here we have F AX, right? Plus FBX plus the force of friction in the x-axis. And I know what you're thinking. You're thinking it's all in the x-axis. Yes, okay, sure. But I'm just going to show that I'm adding up the x components of everything. Okay, so what is FAX really? Well, if we go up here to our kind of free body that we've drawn where we've separated the components, FAX. Okay, I'm going to make this bigger because that's kind of too tiny, right? We have FA, we have FAX, and we have FAY, right? And we know this angle is 20 degrees. They also gave us FA, we haven't written it down yet, but it equals 10,000 newtons. Okay, same actually goes for FB. I'm going to have to draw it eventually, so might as well do it now. FB is here. Okay, FBX looks like this. And FBY looks like this. Okay, so again, from the diagram, this angle is also 20 degrees. These triangles are kind of mirror images of each other, right? How do I get the x components of FA and of FB? Well, we got to use a trig ratio here, right? So let's think about it. I want FAX, right? I know FA, so FAX to theta is the adjacent side, right? And that is the hypotenuse. So adjacent hypotenuse, so toa, right? So cos was going to be the useful one here. FA, or we have that cos theta equals FAX, the adjacent side, over FA, not just theta, I guess it's cos 20, right? Same goes for FBX, right? It's the adjacent side and the hypotenuse. So cos, I'll write it for real this time, cos 20 equals adjacent FBX over hypotenuse, FB, right? So again, if I wanted FB, whoops, that looks like a Y. If I wanted FBX, what do? I need to multiply both sides by FB so that FBX would be FB times cos 20. Same goes for FAX. FAX would be FA times cos 20. So FAX would be FA cos 20 degrees plus FBX would be FB times cos of 20 degrees, okay? And now the force of friction in the x-axis, okay, is just the force of friction. What is the x component of this force here that's entirely in the x-axis? It's just that force, right? It's all in the x-axis. So plus, we'll just change that to the force of friction. And what must these all add up to? 0. Okay. So now it's time, before we move on too much further, I just want to make a definition here, right? Because we always add vectors. It's just that some vectors will be negative in our coordinate system. So I'm going to go ahead and define this direction as positive and this direction as negative. So looking at that, which are positive here? Is FAX positive? Is FBX positive? Or is FX positive, right? Maybe all three, maybe none. Okay, so take a second, think about that. But the answer is FAX is this way, so it's positive. FBX is this way, so it's positive. But FFX is working against them, so it's negative. Okay, so I'm just going to use that to define my system here. Okay, let's just solve for FF. After all, that's what we're looking for. So what is happening to FF, the force of friction? Why is it not isolated? Well, this is being added to it, and this is being added to it. So we have to undo those additions. We have to get rid of them, right? So we're going to subtract FA cos 20 and subtract FB cos 20 from both sides. See you later, see you later. Okay, but I can't do that to one side and not the other, so minus FA cos of 20 degrees minus FB times cos of 20 degrees. Okay, so what are we left with? The force of friction that must be present here if the net x force is 0, FF equals negative force A cos 20 degrees minus FB cos of 20 degrees. And so the force of friction must be equal to, we know all these things, so we can plug them in. Negative, what's the force, the force applied by tractor A? Okay, well, it's positive, right? It is positive. This negative here is not part of that. It's positive 10,000 newtons times cos of 20 degrees, right? Okay, minus, again, FB is 10,000 newtons, just times the cos of 20 degrees. So we're going to get negative 10,000 cos 20 minus 10,000 cos 20. Okay, again, you can kind of see it's negative 2 times 10,000 times cos 20. That's just because they're the same size, right? Because of the symmetry here. So the force of friction will be equal to, I'm getting negative 18,793.8524 newtons. Okay, what does that negative mean? Does that right? Always, if you get a negative, think about it. Is that what we expected? Well, we said this direction was going to be positive, right? Which way is friction? The opposite direction. So it should be negative. Okay, that's good. Okay. So if this thing is moving in with constant uniform motion, it's not accelerating. Okay, we know how hard A is pulling in the X. We know how hard B is pulling in the X. And so we can figure out what must friction be doing to undo both of those, so to speak. Okay. Okay, so I'm just going to write to the proper number of sig digs here. I was actually given a lot here because the only number I'm actually really given is 10,000, right? Which is 5 significant digits. So we will just say, we can't actually say what the negative means. There's not enough information here to say if that's west, left, south, down, whatever, right? I mean, obviously not down, but the best we can kind of do here is say that the force of friction is equal to negative 18,794 newtons.